Today I'd like to look at these exponential indeterminate forms, 1 to the infinity, 0 to the 0, and infinity to the 0. So first of all, keep in mind that these are forms. This isn't just the number 1 raised to a very large power, because that would be 1. But we're talking about something that's headed to 1, getting closer and closer to 1, something getting closer and closer to infinity in that case. So we're talking about the base wanting to make it 1 by heading towards 1. The exponent wants to make it get very, very large, assuming we're approaching 1 from above. So numbers slightly bigger than 1. If the numbers are slightly smaller than 1, then raising to larger and larger powers actually wants to bring it down to 0. So still there's a battle there. Is it heading to 1 or is it heading to infinity if these are slightly larger than 1? Or is it headed to 1 or is it headed to 0 if these are slightly smaller than 1? So it depends on the rate. Again, here, 0 to the 0. And it's easiest to think of this for positive numbers, so everything's defined. But if you're looking at positive numbers close to 0, the base wants to make that 0, of course. But if the exponent's getting close to 0, when you take numbers very close to 0 to very small powers, think about taking square root, cube root, fourth root, fifth root, you actually make it bigger. And think about what raising to the 0 typically does. It makes it 1. So the base, as the base heads to 0, it's pulling that quantity to 0. As the exponent heads to 0, it's pulling that quantity up to 1. So again, it's a battle whose effect is stronger there. And then again here, the base wants to make that quantity very, very large because it's heading to infinity. The exponent's trying to bring it down to 1 by heading to 0. All three of those cases are indeterminate. None of them are in the form that we can use L'Hopital's rule on, but all of them can be put into the form of L'Hopital, either 0 over 0 or infinity over infinity. We'll approach all three of these the same way. We need to remember a couple of things. Recall that e and natural log of x, we defined natural log of x as the inverse of e to the x. So we're going to take advantage of that property. We're also going to take advantage of the property of logs, that natural log of a to the b is b times natural log of a. So those two things together will allow us to manipulate our original limit so that we can get it into a form that we can use L'Hopital's rule. So first of all, let's look at an example of how this would go. So say we had the limit as x goes to infinity of 1 plus 1 over x to the x. So as x gets very, very large, that little fraction's going to 0. So you have 1 plus 0, which is 1. So the whole base is headed to 1, but the exponent's headed to infinity. So we're looking at that first indeterminate case there. So I just want to remind us that what form we're dealing with the form of 1 to the infinity. Okay. So the first thing I'm going to do is introduce e in natural log. So this is equivalent to e to the natural log of the limit as x goes to infinity of 1 plus 1 over x to the x. Right? Because of those being inverses, they cancel each other off. We have to be a little bit careful. Obviously, it has to be defined. Right? Natural log of x is only defined for positive x's, so maybe let's just remind ourselves of that right here. We're talking about when x is defined. If x is -2, then this isn't even defined, so they don't cancel off. But let's think about what we have here. This is 1 plus a positive quantity, so it is positive, and then you're raising it to a power. So what we have inside there is greater than 0. The argument is fine. Okay, now I want to use a property of limits we had previously in Calc 1 that said that I could bring that log inside the limit, or conversely think of bringing the limit outside the log there because it's a continuous function. We called that the continuous function theorem of limits. So that's next here. I'll exchange the limit, bring the log inside. Now the point of all that is to end up here. We want to get that function out of the exponent, so now that this is log of a to the b, that exponent can come down in front. So all right, now what do we have? As x goes to infinity, this is headed to infinity. The argument here is headed to 1. Natural log of 1 is 0. So now we have a form infinity times 0, which is an indeterminate form we looked at previously. And if you recall, the idea was to take the reciprocal of one of those functions and put it on the bottom so we could get a L'Hopital form. And usually one way works and the other one doesn't, and always go with the easier looking way. So I'm going to take the reciprocal of the easier looking function there, just x. So we have e to the limit as x goes to infinity, natural log of 1 plus 1 over x over 1 over x. So 1 over x is the same as x, so that's just an algebra manipulation. It's equivalent to what we had before. But what do we have now? This is of the form, as we head to infinity, that's heading towards 1. Natural log of 1 is 0. As we head to infinity, this is heading to 0. So we've gotten it into that form 0 over 0. So L'Hopital's rule applies. So let's do that. Natural log, we have a composition. There's a function in there, so we have chain rule. So 1 over that inside plus, times the derivative of the inside by chain rule. And then on the bottom, the derivative of the bottom, also negative 1 over x squared. And remember, I want you to say by L'Hopital's rule when you use it. Now those two will cancel. And we just have e to the limit as x goes to infinity of 1 over 1 plus 1 over x. And now finally, that is not indeterminate. As x goes to infinity, that's headed to 0. You have e to the 1 over 1 plus 0, or just e. And there we have it. And depending on the form, it may end up that you have to do something a little different here in the middle, depending on what it looks like. But these first few steps are always the same. You're going to introduce e to the natural log of the limit, exchange the log in the limit, and then allow yourself to be able to bring that exponent down. And then from there, you just follow whatever approach we've seen previously. This limit is a particularly interesting one. I picked this one on purpose in that in algebra, this is probably how you were introduced to what E is. If you recall, you looked at the idea of compound interest, and then what happens as the number of compoundings goes to infinity. And you saw that that formula sort of magically transitioned from this exponential of some natural base to this, some rational base to this irrational e. And in algebra, we really couldn't explain to you where that's coming from, but it's really what happens in the limit of that. Often, this is how e is defined often, because this is initially, this is where e was first encountered historically, was in trying to see what happens in that limit, and they were looking at compound interest. So that is the context in which E first arose in mathematics. Here in calculus, we started off defining E a little bit differently. If you recall, we defined E as the base of the exponential. So let's just remind ourselves what we really have proven about E so far in this sequence. We initially defined E to be by saying that, well, there's some exponential who at 1 here, or at 0, the slope of the tangent line is 1. Whatever that base is, we were calling that E. That was our definition. Well, and that definition is great from a calculus perspective because that allowed us to get the derivative of exponentials. But through everything we've done so far, we've arrived at the definition that you would have in algebra. So that definition leads to this one. So we're able to derive that. So now this definition, which was great for finding derivatives, but not so great at telling us what E actually was, right? This in no way tells you how you could compute E. But now we see that if we just plug in larger and larger x values into that expression, we'll get better and better approximations for this irrational quantity E.